Hello everyone, welcome to section 7.1 on trig identities. Well, really, welcome to chapter 7. In chapter 7, what we're going to start doing is we're going to start doing what's called analytical trigonometry, which just means that we're really going to start approaching trigonometry from a more algebraic point of view. So what does that mean? That means we're going to be doing a lot of algebraic manipulations. We're going to have a lot of trig identities. We're going to have a lot of formulas. I'll try to be very clear on formulas that you should really be paying attention to, ones that you should have, memorized, and then the formulas that you should know exist and just know how to use them. So what I first want to do in this video, a little bit of this will be a review, but I want to list what we call the fundamental trig identities. Now there's ones here we already know, and there's going to be some new ones that we'll learn. Okay, so let's first begin about the trig identities that we need to know. So first of all, where did we start, or where does trigonometry really come from, or what is its foundation? I would really say it comes from SOHCAHTOA. We really am building this whole class from SOHCAHTOA. So we have some old hippie, got another hippie, tripping on acid. So we know that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So I guess what I'm going to write here, we'll kind of keep this here, but we're going to be talking about the fundamental identities. Let's actually move this up here and give ourselves a little bit more room. The fundamental identities. Okay, the first ones we're going to talk about are the reciprocal identities. Okay, so we're already very familiar with these ones here. Specifically, let's talk about, how about secant? Okay, secant of theta is defined to be 1 over cosine. So what this means is cosine is adjacent over hypotenuse, so secant of theta is defined as hypotenuse over adjacent, or it's the reciprocal. Similarly, we have that cosecant of theta is 1 over sine of theta. So sine is defined as opposite over hypotenuse, cosecant is defined as hypotenuse over opposite. Similarly, we have that cotangent of theta is equal to 1 over the tangent of theta. So this means that tangent is opposite over adjacent, so cotangent is adjacent over opposite. So we're already really familiar with these. Okay, there's another two, which hopefully we're familiar with. Specifically, that tangent of theta is equivalent to sine of theta over cosine of theta. Now, when I first, introduced this trig identity, I think I introduced it in terms of the unit circle. So maybe I'll do it two different ways for you. If we're on the unit circle, okay, if we rotate an angle theta, let's say we're right here. Okay. So this length here, this would be the x coordinate. This would be the y coordinate. On the unit circle, this length here is 1. Okay, so we have that sine of theta. So if this is theta, we have a nice right triangle here. Well, sine is opposite over hypotenuse, so it's y over 1. Or sine is just the y coordinate. Similarly, cosine of theta. Cosine is adjacent over hypotenuse, so that's x over 1, which is just x. And we could also see that tangent of theta, well, tangent is defined to be opposite over adjacent, so that's y over x. So that's equal to y over x. So let me kind of move my camera a little bit. So tan of theta is the same thing as y over x. Well, y is the same as sine, and x is the same as cosine. So we have this famous identity that tangent is the same as sine over cosine. Maybe a different argument for the same thing that doesn't have to do with the unit circle, if you'd like. I'm going to go ahead and erase this. Well, let's think over here. Okay, what is sine defined as? Sine is defined as opposite over hypotenuse. So I'll put opposite over hypotenuse. That's what sine is. Cosine is defined, maybe I should draw a triangle right here. So we're standing here. Okay, this is opposite, this is adjacent, and this is the hypotenuse. Okay, well, sine is defined as opposite over hypotenuse. Cosine is defined as adjacent over hypotenuse. Okay, well, notice here I have a fraction divided by a fraction. Remember how we divide fractions as we flip and multiply. So this is the same thing as opposite over hypotenuse times hypotenuse over adjacent. I'm just flipping the bottom fraction and multiplying. Okay, well, notice when these multiplies together that the hypotenuses cancel out and we're just left with opposite over adjacent, which is exactly what tangent is. So I've just shown that if I take sine and I divide it by cosine, and I use their definitions from SOHCAHTOA, and just do a little bit of algebra here, sine divided by cosine is equivalent to opposite over adjacent. We have a definition for that. It's tangent. So there's a non-unit circle argument for it. It came directly from SOHCAHTOA. Okay. So we have that tangent. We have that tangent. Tangent of theta is sine of theta over cosine of theta. And we also have that since cotangent is 1 over tangent, this means that cotangent is equivalent to cosine of theta over sine of theta. Okay, I know we've seen this before, but what's going to be really important for us is specifically looking at these and looking at these. This is what's really nice. This is what's really nice. So in our head, we should think to ourselves, wow, every trig function can be written in terms of sine and cosine. So not necessarily both of them. So I can take any trig function and I can write it in terms of sines and cosines, and that's really great here. Secant can be written in terms of cosine. Cosecant can be written in terms of sine. Tangent can be written in terms of sine and cosine. Cotangent can be written in terms of cosine and sine. This is really going to help us when we start messing around with trig identities. Things that are a little bit more complicated, or we're going to start simplifying trig expressions, we're going to start proving trig expressions, and one of the best tools that we have is to take trig functions and write them in terms of sines and cosines. This will be one of our best tools. Okay, so now another great set of identities that we need to have memorized. We need to know these. Ones that we should have in our brain and never let go of are the Pythagorean identities. These aren't going to go away anytime soon. The Pythagorean identities. Okay? So they're called the Pythagorean identities because they come from the Pythagorean theorem. So if you remember me talking about these in the past, I made it all through grad school, really just knowing the ones, the trig identities I'm about to show you. Really the one trig identity that I really got all the way grad school with knowing is just that sine squared plus cosine squared is equal to 1. Okay, that's the one that makes the most sense to me. Why? Because it's really just saying, hey, Pythagorean theorem on the unit circle. So if we're right here, we rotate an angle theta, we just learned that the x-coordinate, that the x-coordinate on the unit circle is the same thing as cosine of theta, this is 1, and the y-coordinate is the same as sine of theta. So if we use the Pythagorean theorem, the sum of the square of the legs of a right triangle is equivalent to the square of the hypotenuse. So this says that sine squared of theta plus cosine, and I'm going to do this again because students always struggle with this notation. If I take sine squared plus cosine squared, sine squared plus cosine squared is equal to 1 squared. That's what the Pythagorean theorem on the unit circle. Well, whenever we talk about squaring a trig function, it's not very common to put the power here. It's very common to put the power right here. So we'll write this as sine squared of theta plus cosine squared of theta. 1 squared is the same as 1. This is the first Pythagorean identity. Okay, we know this one. We get 2 for free. We get 2 for free. Okay, how do I get the other 2 for free? We just do some massaging. Okay, what would we like? Well, I would really like, let's say, for tangent to show up. But I remember that tangent is the same as sine over cosine. So how about we divide everything by cosine squared of theta. Here I'm just dividing both sides by cosine squared of theta. Same thing as dividing all the pieces. Okay, well, let's think what we have here. Well, if I'm going over a lot of gory detail here, notice here that if I have A over B quantity squared, that's the same thing as A over B times A over B, which is the same thing as A squared over B squared. So this is equivalent to sine of theta all over cosine of theta quantity squared. Plus, this is just cosine squared over cosine squared. Well, that's just 1. And this is going to be equal to, if you would like, you could think of this as a 1 is the same thing as 1 squared. So you could think of this as 1 over cosine of theta quantity squared. Okay, cleaning this up here, I'm showing a lot of gory detail here. Sine over cosine is the same thing as tangent. So this is tangent of theta quantity squared plus 1 is equal to, well, what's 1 over cosine? That's secant of theta quantity squared. Or we have that tangent squared of theta plus 1 is equal to secant squared of theta. Again, I'm using that notation that when we square, or even if we cube, or even if we take a trig function to the 100th power, we don't write the powers here, we always write the powers here. Okay, so this was a lot of gory detail. Usually when I'm memorizing this or I'm going through this exercise, I don't think about this much gory detail, but I think it's nice to see it. I just think to myself, well, sine squared over cosine squared, that's tangent squared. Okay, cosine squared over cosine squared, that's 1. 1 over cosine squared, that's the same thing as secant squared of theta. And here we have the second Pythagorean identity. Notice I held on to 1. This is like an infomercial. Where they're like, oh, you buy this, you get all these for free. Well, we bought this, or we understand this, and we got this one for free. We got this one for free just by thinking about dividing by cosine squared. Okay, how am I going to get another one, another Pythagorean identity? Well, instead of dividing by cosine squared, divide by sine squared. So if we divide both sides by sine squared, let's say, okay, well, sine squared over sine squared is just 1. Plus, again, you could go ahead and show all the gory detail, but cosine squared over sine squared will be the same thing as cotangent squared of theta is equal to 1 over sine squared will be cosecant squared of theta. So here we have the famous Pythagorean identities. Okay, we have to have these down. These aren't going away anytime soon. What's my recommendation for memorizing this? You should know this. This should make so much sense to you that this is just the Pythagorean theorem on the unit circle, that you should never forget it. Well, what if you forget the other ones? We just did a little bit of algebraic manipulation. We just massaged these a little bit to get the other 2 Pythagorean identities. I have this one memorized, and when I forget these, I quickly derive them, and that's what I recommend you do. Very useful. These are the Pythagorean identities. Here's all 3 of them. Okay. Now, I'm about to show you some new trig identities now. So here are some new identities that we haven't seen yet. These are called the even and odd properties. Okay. These are also incredibly useful to know. I highly recommend them. You should really just know the even and odd properties of sine and cosine, and then you could think about what the even and odd properties will be for the other 4 trig functions. I'll show you what I mean. Okay, let's first recall what it means for a function to be even, if you don't remember. What does it mean for a function to be even? Okay, I'm going to show you an abstract definition, and then we'll go ahead and describe what it says. A function is even if the following is true. If you take a function and you put a negative on the inside of the function, it's the same thing as just f of x. This is what it means for a function to be even. A negative on the inside of the function does nothing to the function. Let's think about what this means. This may seem abstract, but in terms of function transformations, this is what it says. What does it mean when I put a negative on the input of a function? Well, think that I have my inputs of my function, and now I'm saying make them negative. What's that going to do? Well, all my x values are now going to become negative. All my x values, if they were positive, now they're negative. If they're negative, I'm throwing a negative on them, and now they're positive. This is a reflection. This is a reflection over the y-axis. That's what this is saying mathematically. You know, this is in mathish. This is in mathish. In English, this says reflection. Reflection over y-axis. Reflection over y-axis, that's what this says. You're reflecting a function over the y-axis, and this is kind of saying does nothing. Does nothing. Does nothing to f. This is screaming a little bit of a symmetry argument about a function. This says if you take a function and you reflect it over the y-axis, the picture looks the same. You reflect it over the y-axis. So if I gave you a picture of the function and I gave you a picture of the function reflected over the y-axis, you would have no idea. You couldn't tell the difference between them. You couldn't tell which one had been reflected or not. Can you think, maybe pause the video, can you think of a couple functions or some toolkit functions that are even? Well, the most classic example is x squared. X squared is an even function. So let's do a couple examples. X squared, let's say f of x. F of x, which is equal to x squared. This is an even function. We say this function is even. Okay, why? Well, let's just look at the picture. X squared looks like that timeless, that classic parabola. Notice here, if I take this picture and I reflect it over the y-axis, here's the picture reflecting it over the y-axis. The picture is the same. We say that x squared is an even function. It's symmetric about the y-axis. That's what this means here. I'm going to say here, this means symmetric. Symmetric about the y-axis. That's what it means for a function to be even. And when I think of the word even, I think the reason why it gets the name even, now don't quote me on this, but this is how I remember it, as I remember the example x squared. 2 is an even number. Even if this was x to the fourth would still have this general shape. It'd be, a little bit more kind of, it would grow much quicker, so x to the fourth would kind of look a little bit more like this, but in terms of general shape, it still has that parabola type shape. X to the fourth would be even. X to the sixth would be even. These are all even numbers, and they're all symmetric about the y-axis. So that's how I remember even. If I want to show algebraically that a function is even, well, how do I show that x squared is even? This is its definition. I just have to show that this is true. So how can I show that this function is even without looking at a picture? Well, I just asked myself the question, what happens when I throw a negative on the x value? Okay, well, I'm going to replace x with a negative x. So if you would like, this is the same thing as negative 1 times x squared. So if I'm really going to show a lot of gory detail here, I guess, so this is negative 1 times x times a negative 1 times x. Order of multiplication doesn't matter. 2 times 3 is the same as 3 times 2, or 2 times 3 times 4 is the same as 4 times 2 times 3. You can rearrange multiplication however you'd like. So how about I rearrange this to be negative 1 times negative 1 times x times x. A negative 1 and a negative 1 makes a positive 1, so this just turns out to be x squared, which is equivalent to our original function, f of x. So I just showed that f of x, which is equal to x squared, when I throw a negative on the inside, it doesn't affect my function. X squared is even. Okay? Can you think of another function that is even? Another function here that is even. Okay, maybe that's not x squared. Okay, well, haven't talked about our trig functions yet. But another function that is even would be the absolute value of x. The absolute value of x. This is also an even function. That looks like the classic V shape. This function here is even. It's if you take this picture and you reflect it over the y-axis, it's the same picture. It's still a classic V. Okay, so this would be an even function. Okay, you can go ahead and algebraically show this if you'd like, but the absolute value is an even function. If you throw a negative on the inside, I'll be able to show it. The negative absolute value of x, what does the absolute value function do? It doesn't care about negatives. It doesn't care about negatives. For example, this is saying like the absolute value of -3 is equivalent to the absolute value of 3. What does the absolute value do? It takes a number and makes it positive. So the absolute value of -3 is equivalent to the absolute value of 3. So this function is even. One more that at least I can think of off the top of my head would be the classic 1 over x squared. This is the reciprocal squared function. If you don't remember what this function looks like, you should remember what this function looks like. This is the classic volcano. This is a volcano-looking function. So here's the reciprocal squared function. Notice here that this function is symmetric about the y-axis. And again, hopefully you can see here that 1 over that f of negative x, which would be 1 over negative x, I'm just replacing the x with a negative x. Well, this is equivalent to 1 over x squared, I hope you believe, which is just f of x. So notice here that the reciprocal squared function is also even. Okay. This now leads us, though, to thinking about which one of our trig functions, if we think about their graphs, which one of our trig functions is even? Cosine's even. Take a look at its picture. Let's take a look at its picture. So this is the big news. This is the big news. We now kind of understand what to do with negatives and cosines. So cosine, f of x, which is equal to cosine of x, is an even function. Let's just think about its graph. Remember cosine? Cosine looks like this. Notice here that cosine is symmetric about the y-axis. So cosine is an even function. What we have here is that the cosine of x is equivalent, the cosine of negative x. What do we do with negatives on the inside of cosine? Nothing happens to them. Cosine is an even function. This is our first even-odd property of trig functions, that cosine is an even function. You throw a negative on the inside of a cosine function, it does nothing. This function is symmetric about the y-axis. Okay, here's a unit circle argument for the same thing. Here's a unit circle argument. Okay. So if I draw the unit circle, okay, maybe instead of using x's, it would be the same thing if I said the cosine of negative theta is equivalent to the cosine of theta, just doing a variable change. Well, if we rotate an angle theta, let's say we rotate an angle theta, well, rotating an angle theta, what if we rotated a negative angle theta? That just means we're going in the opposite direction. So it's not a perfect circle here, but this would be negative theta. Now remember what cosine measures. Cosine measures the x-coordinate. Notice, for both of these, they would give you out the same cosine. So this here is the cosine of theta. This here would be the cosine of negative theta. Okay, and I guess I could put sine of negative theta here. But the idea here is, remember, cosine spits out the x-coordinate, and the x-coordinate for both of these angles is equivalent. So here's a unit circle way to see that the cosine of negative theta is the equivalent to the cosine of theta. They both spit you out that same x-coordinate. So you can think about it graphically, or you can take a look at the unit circle. Cosine is an even function. Cool. Okay. So we're going to hold on to this one. Cosine of negative x is equal to cosine of x. It's an even function. Okay, what does it mean for a function to be odd, though? Odd. Odd. Okay, I'm going to erase this right here. We'll write it back up in here in just a moment. What does it mean for a function to be odd? Okay, well, here's the formal definition. A function is odd. It says that if I put a negative on the inside of the function, that's equivalent to putting a negative on the outside of the function. This is what it means for a function to be odd. Okay, so this is very mathy. This is where I'm speaking to you here. I'm speaking to you here in mathish. But what does this say in English? What does this say in English? This says, just like when we were talking about even, this says a reflection about the y-axis. I'm taking a function, I'm taking its x values, and I'm making them negative, so that just reflects my graph over the y-axis. If a function is odd, is it saying that if I reflect a function over the y-axis, okay, now what is this telling us? Maybe I'll put it in green. What is this telling us? Well, now I'm putting a negative on the outside of the function, so now I'm affecting the outputs. That means if I had a positive output, okay, so just regular f of x, if I had a positive output, now I'm making it negative, I'm going to have a reflection over the x-axis. Or if I had a negative output and I throw a negative on it, that's going to make it positive. So when I throw a negative on the outside of the function, that reflects it over the x-axis. So this is a reflection about the y-axis. Okay? What this says here is that if I take the graph and I reflect it, if I reflect it this way, you would get the same picture as if you reflected it this way. If you reflected it this way. So if I gave you a picture and I said a graph and I said, hey, I reflected this picture over one of the axes, is it the x-axis or the y-axis? You wouldn't be able to tell which one it is. It could be either or. You wouldn't know. So what is a classic example of an odd function? X cubed. So here is the most classic example and how I remember them. So f of x, which is equal to x cubed, this is an odd function. Okay, I wouldn't say odd in terms of like being strange. It's, you know, x cubed isn't a strange function. It's odd. It's odd in terms of this symmetric property. And again, I think that it gets the word odd because a perfect example is x cubed, and 3 is an odd number. At least, I don't know if that's how they came about, but that's how I think about it. Okay, so here is x cubed. Notice here, so I'll just do it with my hands. I'll try to just convince you with my hands. Okay, here's x cubed. Here's x cubed. Okay, so if I reflect it over... if I reflect it over the y-axis, I get this picture. Reflected over the y-axis, I get this picture. So if I'm reflecting it this way, the picture would look like this. Okay, reflection over the y-axis. Is that the same picture if I reflect it over the x-axis? I'm trying to show you. Is this the same picture? Is it the same as this picture? Yeah, I hope so. I hope you see this. If I take this piece and I reflect it this way and get this green picture, it'd be the same as me reflecting it this way. So I hope you see here that x cubed is an even function. Reflecting it over the y-axis is the same as reflecting it over the x-axis. Okay, how can I show, if I want to show this a little bit more algebraically, well, how could I show that f of x cubed is odd? Well, what happens when I throw a negative What happens when I replace x with a negative? Okay, if I want to show a lot of gory detail here, this is -1 times x being cubed. This is equivalent to, I could be using some exponent properties here. Just trying to show some super gory detail. Okay, that's what it means to cube something and multiplying it by itself 3 times. Order of multiplication doesn't matter. This is the same thing as -1 times -1 times -1 times x times x times x. Well, -1 times -1 is a positive 1 times an extra negative is a negative. This is the same thing as a negative x cubed, which is equivalent to having a negative on the outside of the function. X cubed is the same thing as f of x. This is negative f of x. So putting a negative on the inside of the function is the same as putting a negative on the outside of the function. Reflecting it over the y-axis is equivalent to reflecting it over the x-axis. Beautiful. Okay, can we think of another good function? It's maybe not a trig function quite yet. That's odd. Well, I hope you believe also that x to the 5th, if you think about the graph of x to the 5th, x to the 5th should have still that general shape of the cubic. It'll just grow a little bit quicker. And same thing with x to the 7th, and so on and so forth. X to the 101 too. How about 1 over x? Classic. 1 over x. Okay, 1 over x. I hope we know what this one looks like. This one looks like this. This one. This is the classic 1 over x function here. Notice that reflecting this graph over the y-axis, if we reflect it this way, it would be the same thing as if we reflected it this way. So I'm not drawing them on top of one another, but I hope you see the pictures would be the same. 1 over x is also an odd function. Okay, with this in mind, can we think of one of our trig functions that is odd? Sine. Sine is odd. Sine is odd. Okay. Let's draw sine. Okay, just a loose sketch. Remember sine. See how much I want to draw. Should be enough for the picture. How about we just draw? Yeah, sure, we'll keep going. Sure. We'll keep going. Okay, here's a rough picture of sine. Notice if I take the sine graph and we reflect it, if we reflect it over the y-axis, reflecting it this way, over the y-axis is equivalent to us reflecting it over the x-axis. So the green, I'm reflecting it this way. The blue, I'm reflecting it this way. Same picture. Sine is an odd function. We have that sine of negative x is equivalent to the negative sine of x. So if we ever have a negative on the inside of a sine, we can move it out front, which is really nice to be able to do. Sine is an odd function. Okay? Okay, let me give you the unit circle argument for it. Okay, I'll draw that same picture we had just a moment ago. Okay, so here's our unit circle argument. Instead, how about x's, how about thetas? Just a variable change. Okay, so here is theta, and here is negative theta. Okay, so here is the x-coordinate is cosine of theta, and the y-coordinate is sine of theta. Okay, over here, this would be cosine of negative theta, which we know is the same thing as cosine of theta. We just learned that. Okay. Well, if I think about what is sine of negative theta is this value right here. Be this height, be this negative height here. Well, what is sine of theta? Well, sine of theta is this value here. Here's sine of theta. So if I think about sine of negative theta, this is sine of negative theta. But if I do sine of theta, I get this output. But then if I make it negative, I'm just reflecting it over this axis here. So sine of theta, if it's positive and I throw a negative on the outside, now I'm right here. But that's the same thing as doing sine of negative theta. So there's a quick argument. So this height right here, this right here, is sine of theta. That's this height here. Well, this right here will be the same thing as negative sine of theta, taking this y-coordinate and making it negative, which would be equivalent to the sine of negative theta. So sine is an odd function. Cool. Okay, I'm going to go ahead and erase what we have here. Okay, so let's write these up. Let's write these up. Okay, we have evenness. We have functions that are even. What are our even functions? Well, we know that cosine of negative x is equal to the negative cosine of x. Okay? Well, from here we could take a look at the graphs of cosecant and secant and those ones, but we actually can quickly think about what other trig functions would also be even. Well, if cosine is even, it's probably not a surprise that it's reciprocal. Reciprocal secant is also even. And let me show you that. It turns out that secant is also even. If I do secant of negative x, okay, let's see what happens. Well, using that reciprocal identity, this is the same thing as 1 over cosine of negative x. But because cosine is even, this is the same thing as 1 over the cosine of x. But 1 over cosine is the same thing as secant of x. So I've hopefully just shown you that it's also true that secant of negative x is equal to the secant of x. So secant is also even. We could also see this from the graph of secant. Okay, so the way I think about secant is I think about reciprocating cosine. So here's a rough sketch of cosine. If I'm thinking about, remember, secant is 1 over, so any place where cosine is 0, the x-intercepts of cosine become vertical asymptotes of secant. So if we're sketching secant, hopefully you recall that this here in green is a rough sketch of the graph of secant. Notice if we reflect it over the y-axis, the picture would be the same. Secant is an even function. But I was able to remember that secant was an even function. I didn't have to remember its graph. I just remember that cosine was even, and I could quickly see that secant would also have to be even. Cool. Okay. Fun. Okay. Let's look at ones that are odd. Okay, what do we know so far? Well, we learned that sine is an odd function. Sine of negative x, what can I do with negatives and sine? I can bring them out front. Okay, now the question is what about we have 3 trig functions up here. There's 3 more we need to think about. What about tangent, cotangent, and cosecant? Well, I hope you're not too surprised that if sine is odd, then cosecant must also be odd. So cosecant, we can just show that really quick. Cosecant of negative x, let's show that it's odd. Well, cosecant is the same as 1 over sine of negative x, but we know that sine is odd. What can we do with negatives and sine? We can move them out front. Okay, so this is a negative. Think of it as -1 times sine. In a fraction, it doesn't matter where you put a negative. Saying that negative a over b, this is equivalent to saying a over b but have a negative in the middle. This is equivalent to a over negative b. It doesn't matter where you put a negative in a fraction. So how about I just move this out front? This is the same thing as -1 over sine of x. which is the same thing as negative cosecant of x. So I hope you see that what can we do with negatives and cosecants? We can move them out front. This means that cosecant is an odd function. Now, I highly recommend you draw the graph of cosecant to see the symmetry of it. Okay, this is saying that if you take the graph of cosecant and you reflect it over the y-axis, it's equivalent to reflecting it over the x-axis. That's what that says. Okay. Now, if you take a look at the graphs of tangent and the graphs of cotangent, I hope you would see that they would be odd. Remember that the graph of tangent, again, maybe we'll sketch it really quick. How do I remember the graph of tangent? Well, I remember that tangent is the same as sine over cosine. Sine is the height on the unit circle. Cosine is the width on the unit circle. Tangent is sine over cosine. So tangent is rise over run. Sine over cosine. Tangent is the slope on the unit circle. So as we rotate around, what's tangent doing? As I'm putting tan of x, you could put theta here. Well, if we're over here at pi over 2, as we rotate around, the slope of this line gets larger, and it gets infinitely large till we get to pi over 2. Okay. And if here's negative pi over 2, if we're rotating negatively, we now have a super negative slope, and it's getting more and more and more negative. So here's one period of the graph of tangent, and it's just going to repeat itself. So hopefully you can see just from the graph that if you took this picture and you reflected it over the x-axis, it'd be the same as reflecting it over the y-axis. So tangent is an odd function. We'll have that the tangent of negative x is equivalent to the negative tan of x. And it would also be true for cotangent. I highly recommend you take a look at the graph of cotangent. But it also turns out that cotangent is also an odd function. Make sure to go take a look at the graphs of those. Okay, but, I mean, you can remember these graphs, but we could actually, since I just know that cosine is an even function and sine is an odd function, and remember we can write any trig function in terms of sines and cosines, I can figure out the even and oddness of any trig function just by knowing the even and oddness of sine and cosine. So, for example, if we are trying to show algebraically, a lot of times what we're going to be doing in this class, since it's analytical trig, we're going to be doing things algebraically. So if I want to show that tangent is odd, I'm going to put a negative in the tangent, and let's see what can we do here. Well, we know that tangent is the same as sine over cosine, okay? But sine is odd, so I can move the negative out front. Cosine is even. When I put a negative on the inside, it doesn't do anything to it. I can get rid of the negative. So this is the same thing as negative sine of x all over cosine of x. I guess I'm just moving the negative off of the sine and out front. Well, this is the same thing as negative tan of x. So tan of negative x is equivalent to negative tan of x. Reflecting tangent over the y-axis is equivalent to reflecting tangent over the x-axis. I just showed this algebraically. Now, you could do the same thing with cotangent. I think that's a great exercise for you to do. Let's just remember that cotangent is cosine over sine, and you would use the same argument, the same algebra I've done here, just everything would be reciprocated to show that cotangent must also be an odd function. Fun. How fun. Okay, these are great things to remember. Okay, but again, this seems like a long list. But what do I hold on to? I just remember what the graphs of sine and cosine look like, and I think about, is cosine even or odd? Oh, well, if I reflect it over the y-axis, it doesn't do anything. That's an even function. Sine graph. Oh, if I reflect it over the y-axis, it's the same as reflecting it over the x-axis. Oh, it's an odd function. And then I can think about the even and oddness of the other four from there. Okay, that's like half my theme when I was learning math. It's like hold on to very small ideas, some basic ideas, and build everything from them. And that's how that was the way. That's the way I like to do math. I don't like to memorize things. I like to kind of hold on to a few key ideas and build on them. Okay, so what else do we want to talk about? Let's talk about the last set of fundamental properties are what's called the cofunction. the co-function identities. Now, if you haven't already gone back and watched my video on the 6 trig functions on the unit circle, please go check that out. I explain this same idea right here. But for those of you who haven't seen it, and just for completeness of this video, let's go ahead and talk about them. The co-function identities. Okay. Now this kind of has to do with kind of the naming convention for some trig functions. There's sine, and then there's cosine. There is secant, and then there's cosecant. There's tangent, and then there's cotangent. Well, where does that co come from? Co-function identities, what we should be thinking about is what's called a coterminal angle. Not coterminal, not coterminal, what is it? The complement angle. I apologize. Complement angle. That's where it comes from. When you see co-function, you should think complement. The complement function. And not complement as in terms of like, hey, nice hat. Complement in terms of angles. So just a quick thing to think about right here. So when we talked about complement angles, I think in the very first week of the class. So for example, if this right here is, let's say this is 30 degrees, or let's do it in two different, just two different units. So 30 degrees is the same thing as pi over 6 radians. Okay. Okay, well, what would be this other angle right here? This other angle right here, well, the sum of the angles of a triangle add to 180 degrees. Since 90 degrees is taken up with the right angle, these two angles must add to 90 degrees. So this angle here, I don't know, maybe I'll call it phi, for example. Phi must be the same thing as 90 degrees minus 30 degrees, which is 60 degrees. So this angle phi here is 60 degrees. Or if we want to work in radians, since the sum of the angles of a triangle add to 180 degrees, 180 degrees is the same thing as pi radians. So here the sum of the angles of a triangle add to pi radians. Well, half of those, pi over 2 radians, that's taken up in the right angle. So these two angles must add to pi over 2. So we must have that phi, just using a different units, would be the same thing as pi over 2, which is equivalent to 90 degrees, minus pi over 6. Well, this is the same thing as what? 3 pi over 6 minus pi over 6. Just writing half of a pi as the same as 3 pi over 6. Well, 3 pi's take away a pi. What is this? This is 2 pi over 6, or this is pi over 3. So this here is the same thing as pi over 3. We call these complement angles. So we would say here that 30 degrees is complement to 60 degrees. And vice versa. We would also say that 60 degrees is complement to 30 degrees. Okay, we would also say in this picture here, we would say pi over 6 is complement to pi over 3. Okay, so and likewise, pi over 3 would be complement to pi over 6. Okay, so these are complement angles. Okay, so really it's just if you're on a right triangle and you're at one of the non-right triangles, its complement would be the other non-right angle. Okay, so now where do these co-function identities come from? Or the complement function identities. Okay, well let's draw a picture here. Okay, I think the book here uses radians, so I'm going to do this completely in radians. It would work the same thing in degrees. But let's say we have a triangle. Let's say this is an angle theta. This is, a right angle. And let's say this would be phi, but remember, I hope you believe that this would be the same thing as 90 minus phi. Okay, if we're working in degrees, it'd be 90 degrees minus theta. Or how about pi over 2? This would be the same thing as pi over 2 minus theta. So here we have this angle, and this would be the complement angle. Again, these two angles have to add up to pi over 2. Okay, well, notice something. Notice something. Let's say if we're standing right here. If we're standing right here, okay, and I'm just thinking, for example, about, and let's label these sides here, for example. Let's call this side, I don't know, how about we call this y, how about we call this x, how about we call this c? This would be opposite, this would be adjacent, this would be hypotenuse. Okay, well, notice here that the sine of theta is, what is sine? Sine is opposite over hypotenuse. This would be y over c. But let's say we're standing at the complement angle. The complement angle, and I think about the cosine there. So sine, and then there's cosine, the complement of sine. The cosine of, now I'd be at pi over 2 minus theta. Okay, well, what is cosine? Cosine is adjacent over hypotenuse. Since I'm standing here, this is now the adjacent side from this perspective. So it's still going to be y over c. So what we have here is we have our first cofunction identity, that sine of theta is equivalent to the cosine of the complement angle. And that's where it gets its name, cosine. It's like the complement of sine. Okay, so this is one of them. It would also be true, and you can verify this, that cosine of theta would be the same thing as sine of the complement angle. Okay. So what I want you to do is I want you to convince yourself of the other ones. So draw your triangle and do this on your own. But it's also true that if we did the tangent of theta, that would be equivalent to what's the complement of tangent? That's the cotangent. That means complement of tangent. This would be the cotangent of the complement angle, pi over 2 minus theta. And similarly, it would work the other way around. That the cotangent of pi over 2 minus theta, this would be equivalent to the tangent of theta, and the secant of theta, well, secant, and then there's its complement. The complement of secant is cosecant. The cosecant of pi over 2 minus theta, and it would also be true that the cosecant of theta would be equivalent to the secant of pi over 2 minus theta. These are the cofunction identities. These are very nice to have. Okay, how do I remember these? Do I just have this long list in my head? No, I just remember that there, you have a right triangle. You have a right, you have a right triangle. Okay? You really, oftentimes when you have a right triangle, you're only thinking about the other two. There's this angle and there's this angle. Well, if we're here, the other one's the complement of that angle. So then I just think here that the sine here would be the same thing as the cosine here. That's where it gets its name, It's the complement of sine. So I just think of the naming conventions for these trig functions, and that's how I remember these here. So that's all I have for my daughter here is knocking at the door. I'm going to go say hi in a second. But here are our fundamental trig identities. Okay, these are the ones we really need to hold on to. These are the ones that need to be sitting in our pocket when we work from now on. And what we're going to be doing now is we're going to be simplifying trig expressions. We're going to be proving trig expressions and proving trig identities. And what are we going to do? What tools do we have in our pocket for messing around with those kind of things? These fundamental identities. And that's why I spend a lot of time kind of going over these. So anyway, I hope you enjoyed this video. In the next one, we're going to have a lot of fun massaging expressions. We'll see you there. Take care.